Okay, so in 2.4, we're going to talk about what it means for a function to be continuous and talk about how that connects to the idea of limits that we've been talking about. In this opening paragraph, I talked about different things that might connect like sciences or different fields, but I think you guys know the difference between like a discrete set of data and a continuous set of data. There's some data that could be connected with a smooth curve and it would make sense for the context, and then there's some that's not. And so as a really, really basic idea, and this is kind of a silly thing to write down, but it makes it easy to remember what it means to be continuous. Something's continuous if you can sketch the graph without lifting a pencil. So if in any way that graph breaks, jumps, there's a hole, anything like that, you would have to lift up a pen or pencil to draw that. That means it's not continuous. So this section that we're looking at, we talked about limits for a function that it wasn't this exact function, but it was similar to it. We're going to talk about when a function is continuous and when it's discontinuous. So it's really unusual to talk about points where a function's continuous. You would never say like, oh, it's continuous at 3.1 and 3.2 and 3.3 because you're forgetting about hundreds of rational or irrational or any kind of numbers in between. So usually we talk about continuity in a range, and then we talk about discontinuity as individual points. So if we kind of look from left to right, we're going to start with discontinuities first and then kind of point out anything that looks unusual. Okay, so let's point out our discontinuities. Okay, so as we move from left to right, this is a smooth curve, this is a smooth curve. We're imagining what it would be like to try to draw this. Here's my first discontinuity. I would have to lift my pencil up and jump up here in order to continue graphing that, and that happens at x equals 1. Okay, so at x equals 1, it kind of jumps, all right? Then I'm drawing, I get to this point, there's a hole, I would have to jump up here to draw that point. So that makes x equals 2 also a discontinuity. Okay, so then I'm drawing, it comes to a peak here, I draw back down, never have to lift a pencil. So those two are the only discontinuities. Those are kind of the only issue that we can see. And then we don't speak about what happens to the left of 0 or to the right of 4. So we're not going to say it's continuous there, but we're also not going to say it's discontinuous there because we don't know what's happening. Or, that's outside the domain, the graph might just end there. So the discontinuities, let's talk about why there are discontinuities. So this one right here, it looks like as we come from the left, it looks like the function's going to hit 0. And then all of a sudden it just doesn't. And as you come in from the right, it looks like the function value is going to hit 1, and it does, but it's something different than what happens to the left. So the reason this is an issue is because the limit doesn't exist. It's got a left limit and it's got a right limit, but they're not equal, so the limit does not exist. At 2, as we come in from the left, it looks like the function value is approaching 1. As we come in from the right, it looks like the function value is approaching 1. So this limit actually does exist. The limit here actually is 1, where the hole is, but then it jumps up. And so the reason that this is an issue is because the limit, as x approaches 2, of the function is not equal to the function value. So like the function value itself is actually at y equals 2, but the limit is at y equals 1. So that's why this one's a problem, because the point jumps up and does something different than what you expect it's going to do. So continuities basically happen everywhere else. So everywhere from 0 to 1, so we would say this is an or equal to, this is not, because there is a break at 1, and then from 1 to 2, neither one of them have an or equal to because we have breaks at both of these points, and then from 2 on to 4, including 4, because like 0, this is also a closed point. So you mentioned all those as continuities, and all of those points are perfectly fine. And then, like I said, we don't really mention anything less than 0 or greater than 4. All right, so we're going to learn how to classify these discontinuities. So next thing we're going to talk about is whether something's completely continuous or if it has one-sided continuity. So like this point, for instance, point C has two-sided continuity. You come in from the left and it's continuous, you come in from the right and it's continuous, no issues. These points right here only have one-sided continuity. This one's continuous from the right, this one's continuous from the left. So that's how we're going to define some of these. So you say that a function's continuous at an interior point if the limit is equal to the function value. Okay, so if it has a limit and it turns out to be the same value as the function. So like, let me show you just an example. 3 is continuous at an interior point because as you come in from the left, the function value seems to be approaching 2. As you come in from the right, the function value seems to be approaching 2, and it actually does hit 2. We don't need it to hit 2 in order for it to have a limit, but we do need it to hit 2 in order to be continuous. So that's super important. So that's what this definition means. The limit exists and it also happens to be equal to the function value. Okay, so you can say something's continuous at a left endpoint A. So A is the left endpoint of the interval, B is the right endpoint of the interval. So we say one of these two things is true. We say it's continuous at a left endpoint if the limit coming in from the right. So as you approach A from the right, meaning coming in this way, if it's equal to the function value at A, that's left continuous. We say that something's continuous at a right endpoint or right continuous if the limit of the function as you approach B from the left is equal to the function value at B. Okay, so the wording is a little strange because this is continuity from the right, but we also call it left continuous because it's the left endpoint. So being continuous at a left endpoint involves being continuous as you come in from the right, and being continuous at a right endpoint involves being continuous as you come in from the left. So it seems a little bit backwards, but hopefully the picture helps kind of clarify everything. Okay, so if a function's not continuous, we say that there's a discontinuity at that point. And like I said, we are going to clarify all of the different points of discontinuity. So that is an important phrase that, like I said, we will clarify right about here. Okay, so example 2, we are going to talk about the points of continuity and the points of discontinuity. And like I said before, points of continuity, we usually talk about them in a range, and then points of discontinuity, we speak of them as individual points. So this is something, it's called the greatest integer function, that's its real name. A lot of people call it the stair-stepper function. So you can see there are discontinuities all over the place. There's one here at -1, at 0, 1, 2, 3, 4, and if we repeated this function, you know, for as much of it as we could see, you'd see it's got this repetitive process that it has discontinuities at every single integer. And then let's use C. So the letter C will represent each integer. So here's what we want to write down. We're going to talk about any generic integer, so we can use 2 as a specific example here. So let's talk about what happens as we approach each integer from the left. Talk about what happens as we approach each integer from the right. And then talk about what happens for the function at each integer. So like I said, using 2 as an example, as we come in from the left, it actually looks like it's going to be 1. As we approach 3 from the left, it looks like the function value is going to be 2. As we approach 4 from the left, it looks like the function value is going to be 3. So it's always 1 less. So the limit is 1 less than whatever the integer is. And then as you approach from the right, so say you approach 4 from the right, the function is approaching 4. As you approach 3 from the right, the function is approaching 3. So again, that pattern repeats. And from the right, it seems to be approaching the integer itself. Okay, so we've got obviously these differing answers here, and so that's why the limit doesn't exist there. The function value at 3 is 3. The function value at 2 is 2, etc. So if you repeat that process, that's what you get. So the function is not, or I'm sorry, each one of those points is not continuous from 2 sides, but see how the right side matches up with the actual function value. So if you look at this right here, as you approach each endpoint from the right, it it's equal. So this means it's function, or it's continuous at a left endpoint. So each one of these, this is continuous at the left endpoint, this is continuous at the left endpoint. So it is continuous at the left endpoints. Okay, so the function has discontinuities at every single integer, which means the function is continuous for every non-integer. So for each range that looks something like this, from like a C minus 1, I guess, so it looks like that. So like from this one, from 1 to 2, it's continuous at 1, and then it's not continuous at 2. It's continuous at 2, and it's not continuous at 3. So it would look something like that. All right, next thing we're going to talk about is the different categories of discontinuity. So I'm going to give you some sample pictures, different things that could happen. So the first one we're going to write down is being continuous. There's only one way to be continuous. Okay, so I mean, this function I could draw could be absolutely anything. I will just go for a very, very easy line. So this is continuous at every single point in its domain. All right, so you could say it's continuous at 0, you could say it's continuous at 1, whatever. Next type, now we move on to the discontinuities. There's only one way to be continuous. There are 5 ways to be discontinuous. So the next one is called a removable discontinuity. Okay, so we'll do all these, every single one of these. Let's talk about at x equals 0. We'll just keep it nice and simple that way. So at x equals 0, if our graph looks really, really similar to this, but instead of going straight through, let's say it has a hole at x equals 0. We call this a removable discontinuity because it's super, super easy to fix the discontinuity. We call it removable if you could take just one single point, plug it in, and fix the discontinuity. So you'll see the difference when I show you some of the other types. So again, if you could just plug in one single point and fix the discontinuity, that makes it removable. So this is one way to be removable. Number 3 I'm going to show you is a second way to be removable. Okay, so I'm going to draw a really similar graph. It's going to look like this. There's a hole at 0. And then let's say that we take the point and move it somewhere else. That's another way to be removable. So either there's a hole and it's never replaced, or there's a hole and the point is replaced somewhere else. Either way it's removable because, again, you could just pick this point up, move it down here, and it would be a perfectly continuous function. The next type is non-removable. And there are 3 different types of non-removable functions, so we're going to be specific here. This one is a jump discontinuity. So a non-removable jump discontinuity. So these ones, they're non-removable, so they can't be fixed just by replacing a single point. So the jump discontinuity, looks like this. So say the line is just coming along, breaks, and then picks up somewhere else like that. That's a jump discontinuity. So it's like you've got this whole half of the graph and then it picks up and it jumps somewhere else. Not a single point, but a whole section of the graph jumps somewhere else. So that makes it non-removable. It's called a jump discontinuity. Another type of non-removable is known as an infinite discontinuity. And an infinite discontinuity we already kind of dealt with. It's known as an asymptote, a vertical asymptote. So say our function looks something like this. That would be an infinite non-removable discontinuity at x equals 0. You definitely can't fix that just with a single point. It's a vertical asymptote, not really something you can fix like you could fix this point. And the last one, this is a very strange one. This is also in the category of non-removable. This is known as an oscillating discontinuity. And so you've got functions, and we actually saw one with the sine of 1 over x. Let me see if I can flip back and find that one. It was, I don't know if I actually plotted it for you guys anywhere, but it oscillated around, we're here. This one. So it oscillates like crazy in the middle. And if you were to zoom in on that, it just keeps oscillating and oscillating back and forth. And so these ones look crazy, like they just oscillate up and down and up and down. And the closer you get to 0, the more like blurred it gets. And then it just does something like that. And then just like heads towards the line, y equals 0. So again, the closer you zoom in on here, the crazier it's going to get. We call that oscillating. And so the reason we have a discontinuity there is because we can't actually hone in on one point. It's just going to keep going crazy, and it gets really blurry in there because there's so much happening. All right, so let's talk about all the different types of continuous functions. We looked at the different types of discontinuities. You can look at entire categories of functions that are always going to be continuous. So it kind of makes it simpler to figure out whether you can classify something as continuous or not. So we say a function's continuous on an interval if and only if it's continuous at every point of the interval. Okay, so you can pick out entire intervals like we did on the first page where the function's continuous, and then we say that a continuous function is one that is continuous at every point. And then we'll talk more specifically about what the domain part means as we move into these known continuous functions. So investigate the continuity of this function, which we have seen before. Just give it a quick sketch. We've got these like boomerang shapes in the first and third quadrant like that. So there's a continuity issue right here that is known as a non-removable infinite discontinuity. So we would say that it has an infinite discontinuity at x equals 0. So when you're asked about something's continuity, as soon as you state this, like if you say where there is a discontinuity, it's implying that it's continuous everywhere else. So you don't even really have to mention that part. Okay, let's make a list of the known continuous functions. Polynomials. Polynomials are continuous absolutely everywhere. Polynomials will never have holes, they'll never have jumps, they'll never have asymptotes, ever. The next type, rationals, are continuous as long as, so let's write like f of x over g of x, that's the form for a rational function. It's continuous as long as the denominator isn't equal to 0. If the denominator is equal to 0, you're going to have some type of point of discontinuity. The simple absolute value function, continuous everywhere. Picture it, no holes, jumps, anything like that. These next set, I've got 4 that I'm going to write down. Exponentials, those are continuous everywhere. Again, picture an exponential function. There's not going to be any breaks, anything like that at all. Same thing with logarithmics. Now, logarithmics aren't defined everywhere. They're not defined if x is negative, but it's continuous everywhere where it is defined. Trigonometric functions are continuous as long as they don't have any points where the denominator is equal to 0. So remember, like tangent had asymptotes, and that's because there was a place where the denominator was equal to 0. So say if a trig function can be written like this, so long as the denominator is not equal to 0, you're good. Sine and cosine functions, always continuous, no matter what. And then radical functions are good as long as they're defined. Like a square root of x function isn't always defined, but it's continuous where it is. And then composites of continuous functions are also continuous. So say you plug a sine function into an exponential function. That's also going to be continuous because you're combining two continuous functions and you get something that is also continuous. Okay, and our last little bit here before we do AP problems together is just a quick theorem, very, very quick. It says if you know a function f is continuous everywhere and you know a function g is continuous everywhere, if you combine them in various ways, the result is also going to be continuous. So if you add two continuous functions, the result will be continuous. If you subtract continuous functions, if you multiply continuous functions, if you multiply continuous function by a constant, and then if you divide continuous functions as long as g is not equal to 0 when you plug in x equals c. Because this is talking specifically about x equals c. So if f is continuous at c and g is continuous at c, then any of these combinations will be continuous at c so long as g of c is not equal to 0. We know that. That's a rule that's come up a bunch of times. All right, so we're going to deal with these continuity AP problems together.